Paper 1, June 2019. Figure 1 shows an incomplete Born-Haber cycle for the formation of cesium iodide. So we've got two missing lines here, and we've got to write the formulas, including state symbols, the appropriate species on each of these two blank lines. So let's have a look. Something going to cesium gas and iodine, half a mole of iodine as a solid. Well, cesium isn't normally a gas, so enthalpy of atomization of cesium must be here, turning it from a solid into a gas. So cesium solid, half I2 solid stays the same. One of the two species always stays the same. You only ever change one of them in each of the steps in the Born-Haber cycle. So enthalpy of atomization of cesium is this one here, going from a solid to a gas. At the same time, I might as well put plus 79 in alongside, and then I know the value of that enthalpy change here. The other one here, I've got cesium gas, and I've got cesium gas with a plus charge here. This one here must be cesium gas going to cesium gas with a plus charge. That's the first ionization energy of cesium here. So I'm going to take that from cesium gas up into cesium gas with an electron removed, and there's the electron that's come off the cesium gaseous ion atom when it's formed a cesium gaseous ion. And I might as well put the enthalpy value in of 376 here. Now while I'm at it, I'm going to put the enthalpy values of the other ones in. Electron affinity of iodine is when an iodine gaseous atom gains an electron, so that's this one here at 314. Enthalpy of lattice formation of cesium iodide is where you have 1 mole of a gaseous ion, each of the two ions rather, forming a solid ionic lattice, so that's this one here, minus 585. And enthalpy of formation of cesium iodide is where you have 1 mole of the solid formed, so the solid that's been formed, cesium iodide, 1 mole of it from the elements in their standard states, how you'd normally find them in the lab. Well, cesium's a solid and iodine's a solid, a black solid as well. So that's this enthalpy change here, giving out energy. Its next thermic reaction, minus 337, which is this one here. Now, calculate the standard enthalpy of atomization of iodine. So I'm going to start at the bottom here. I'm going to go all the way up here and then down here and return back to this energy level line here. So going up and then down by the same amount, up by the same amount as coming down, it should equal 0. So I'm going from here at the bottom up to this one here. So I'm going to reverse this sign, plus 337. So plus 337, this one's going in the right direction, 79. I don't know this one. This is the one that I'm going to try and find out, the enthalpy of stagnation of atomization, which is when of iodine, that is, when I turn the iodine from a solid into a gas, so that's X. That's X is the value I've got to find out. I've got 376 going in again in the right direction, and I'm coming down, which is in the right direction, minus 314, and coming down again to minus 585. And going from this line here all the way up and all the way down equals 0. Rearrange it, take all the values apart from X over to the right hand side, so I reverse the sign, minus 337, minus 79, minus 376, minus 314 becomes plus 314, and minus 585 becomes plus 585, so X is at 107. The enthalpy of lattice formation of cesium iodide in table 1 value is obtained by experiment. The value obtained by calculation is minus 582. So let's have a look what that one was. Minus 585 by experiment, minus 582. They're not very different at all. They're very, very similar. So this shows that cesium iodide is almost perfectly ionic. It's got no covalent character or hardly any covalent character at all. It's almost perfectly ionic because the values almost match. Use the data from table 2 to show that reaction is not feasible at 298. So I've got to work out the entropy change first of all. So delta S is my entropy change. Entropy of products minus entropy of reactants is used to work out entropy change. So the products, cesium solid is 82.8. half an I2, well, I've got a whole mole, 1 mole of I2 is 117, so half of that is 117 divided by 2. Take away the entropy of the reactants. The reactants is cesium iodide solid, 130. I've got to minus that because it's take away 130, take away the entropy of the reactants, minus 130, and that equals 11.3. But if you look here, it's in joules per Kelvin, joules Kelvin to the -1 here, and my delta H is in kilojoules, so I've got to turn this from joules into kilojoules. Going from a lower unit value like joules up into kilojoules, I divide by 1000, so delta S now I've got as 0.0113, so I've divided 11.3 divided by 1000, I've got 0.0113 kilojoules per Kelvin. I've got the kilojoules and the kilojoules in the right unit value. So delta G is delta H minus T delta S. Delta H is 337. Take away T, the temperature is 298, it's in Kelvin, which is correct. Multiply by 0.0113. 337 minus 3.37, 334 kilojoules per mole. And because that's larger than 0, so delta G is feasible if it's larger than or equal to 0. It's larger than 0, and therefore the reaction is not feasible.